Hello, I am Yasuki Yamazaki at GFZ Potsdam. This presentation is going to focus on whole atmosphere coupling during the September 2019 Antarctic sudden stratospheric warming. This slide compares the famous January 2009 Arctic SSW and September 2019 SSW. The left panel displays the seasonal cycle of Northern Hemisphere polar temperature at 10 hectopascal as derived from Merritt-2 reanalysis. The yellow line shows the climatological mean obtained from the data during 1980 to 2018, and the range between the observed minimum and maximum values is indicated by the gray shading. The red line highlights the year 2009, which shows a large temperature enhancement in January, corresponding to a major SSW event. The right panel shows the polar stratospheric temperature in the same format but for the southern hemisphere. The red line shows the SSW event in the southern hemisphere during September 2019. This SSW involved a large stratospheric temperature variation, like the January 2009 SSW. Both the January 2009 and September 2019 SSW took place under solar minimum conditions, without any major solar events. The important difference between the two events is that they occurred in different parts of the globe in different seasonal conditions. In the southern hemisphere, the occurrence of SSW is not as frequent as in the northern hemisphere, and so whole atmosphere coupling during an Antarctic SSW is not well understood. This study examines the impact of the September 2019 Antarctic SSW on the middle atmosphere and upper atmosphere, with special focus on the ionosphere at low latitudes. This slide gives a summary of the middle atmosphere dynamics during the September 2019 SSW. The panel 1 shows the stratospheric polar temperature variation associated with the SSW at 10 hectopascal, at a height of approximately 30 kilometers. The panel 2 shows the weakening and reversal of the zonal mean zonal wind in the southern hemisphere high latitude at 1 hectopascal, at a height of approximately 50 kilometers. And the panel 3 is a spectrum of geopotential height at mid-latitudes, at a height of approximately 95 kilometers. It shows activity of westward propagating planetary waves with period between 3 and 17 days. It is seen that the SSW was accompanied by enhanced planetary wave activity with periods between 4 and 11 days. The wave activity is most pronounced at a period around 6 days. The westward propagating 6-day wave with zonal wave number 1 is known as the quasi-6-day wave. The quasi-6-day wave is one of planetary waves that are commonly observed in the middle atmosphere. However, the quasi-6-day wave observed during the September 2019 SSW was much stronger compared with the wave observed during the same season in other years. The panel 4 shows latitude versus height structures of the quasi-6-day wave and or MLS geopotential height during the September 2019 SSW. The amplitude and phase are symmetric about the equator, which is consistent with the 1-1 Rossby normal mode. The panel 5 presents the meridional structure of the 1-1 Rossby normal mode and geopotential height, as well as zonal and meridional winds, as predicted by linear wave theory. During this time, prominent 6-day oscillations are observed in the ionosphere. The panels 1 and 2 show variations in the equatorial zonal electric field and plasma density at 20 degrees magnetic latitude. Both data are obtained from the SWARM satellite, around midday. Oscillation with a period of about 6 days is seen in both parameters. The panel 3 shows the amplitude of the 6-day oscillation and total electron content at each local time and magnetic latitude, as reported by Lin et al. 2020. The local time and magnetic latitude structures of the amplitude reflects the pattern of the equatorial ionization anomaly, so it is likely that the ionospheric 6-day oscillation is produced through the modulation of equatorial plasma fountain. The panel 4 shows the corresponding result obtained from the Gaia model. Gaia reproduces the ionospheric 6-day oscillation during the September 2019 SSW. The source of ionospheric 6-day oscillation during the September 2019 SSW is examined through numerical experiments. For this purpose, the neutral atmosphere model of Gaia was decoupled from the ionospheric model, then the ionospheric model was forced with selected wave components derived from the atmospheric model. This way, it is possible to isolate ionospheric effects due to selected wave components. The panel 1 shows the local time versus magnetic latitude plot for the amplitude of the quasi-6-day oscillation and total electron content. For this run, the ionospheric model was forced with waves with period less than 1.5 days. Although this simulation does not include the direct effect of the quasi-6-day wave on the ionosphere, the result is similar to that of the original Gaia simulation. This suggests that the direct effect of the quasi-6-day wave is not the primary cause of the ionospheric 6-day oscillation observed during the September 2019 SSW. The panel 2 is similar, but this time the ionospheric model was forced with waves with period between 5 and 7 days, including the quasi-6-day wave. The result suggests that waves with period around 6 days are not effective in producing the quasi-6-day oscillation in total electron content. The panel 3 gives a zonal wave number versus frequency spectrum from the neutral model of Gaia. At periods less than 1.5 days, there are spectral peaks associated with not only tides but also secondary waves from the nonlinear interaction between tides and quasi-6-day wave. Various secondary waves are expected to arise from the nonlinear interaction between tides and quasi-6-day wave. For example, the quasi-6-day wave interaction with migrating diurnal tide can lead to 29-hour standing wave, and 21 westward propagating 21-hour wave with zonal wave number 2. Similarly, the quasi-6-day wave interaction with migrating semidiurnal tide can lead to westward propagating 13-hour wave with zonal wave number 1, and westward propagating 11-hour wave with zonal wave number 3. Interestingly, these secondary waves have an apparent period of 6 days when they are sampled daily at a fixed local time. Thus, they are likely source of the quasi-6-day oscillation observed during September 2019 SSW. In search for direct evidence for ionospheric signatures associated with the secondary waves due to quasi-6-day wave-tide interactions, UPC total electron content maps with time resolution of 15 minutes are used. A spectral analysis is performed at each magnetic latitude using a 21-day window. This slide shows Fourier spectra of total electron content at 20 degrees magnetic latitude during 10 to September 30th of different years from 2011 to 2019. The panel 1 is for zonal wave number 0, or standing oscillations. The panel 2 is for westward propagating waves with zonal wave number 1. In each panel, the horizontal axis shows frequency. The frequencies 1, 2 and 3 correspond to diurnal, semidiurnal and terdiurnal tides. The frequencies corresponding to secondary waves due to quasi-6-day wave interaction with tides are indicated by vertical dashed lines. During 2019, when the SSW took place, a spectral peak is seen at 29 hours for the zonal wave number 0, corresponding to the secondary wave due to the nonlinear interaction between the migrating diurnal tide and quasi-6-day wave. The amplitude of this 29-hour zero wave is significantly larger than that during other years, which is indicated by the green shading. In the spectrum for westward propagating zonal wave number 1, a spectral peak is seen at 13 hours. The 13-hour W1 wave corresponds to the secondary wave due to the nonlinear interaction between the migrating semidiurnal tide and quasi-6-day wave. The wave signature is again significantly larger than that of other years. The amplitude and phase of 29-hour zero wave and 13-hour W1 wave in total electron content are plotted here as a function of time and magnetic latitude. For both wave components, there is an amplitude peak on both sides of the magnetic equator at about ± 20 degrees magnetic latitude. Also for both waves, the phase tends to be symmetric with respect to the magnetic equator. The results suggest that these wave signatures in total electron content are produced by modulation of equatorial plasma fountain. It is also noted that the secondary wave signatures are enhanced when the quasi-6-day wave, shown in the panel 5, is strong. Summary and conclusions. The September 2019 Antarctic sudden stratospheric warming was accompanied by unusually strong quasi-6-day wave activity. During the SSW, the equatorial electrojet and low-latitude total electron content at fixed local time showed 6-day oscillations. Gaia suggests that ionospheric 6-day oscillations are not due to direct effect of quasi-6-day wave, but due to indirect effect by quasi-6-day wave-tidal nonlinear interaction. Secondary waves arising from the quasi-6-day wave-tidal nonlinear interaction, such as 29-hour 0 and 13-hour W1, produce total electron content perturbations of up to 8% of the zonal mean. These secondary wave signatures in the ionosphere result from modulation of equatorial plasma fountain. Thank you for your attention. Full details of our study presented in this presentation can be found in these papers. Also, if you have any questions, feel free to directly contact me.